All right. Hi, everybody. Boo, that was pretty terrible. Come on, try again. Hello, everybody. That's markedly better. Thank you. I appreciate that. All right, my friends. Well, welcome. I appreciate you being here. I know there are a lot of other places you could be right now, and yet you chose to come here. I appreciate that. So thank you so much for coming. We're going to go through a lot of stuff today. We're going to talk about, the latest and greatest in cloud-native Java, obviously, and actually cloud-native JVM languages in general, right? Reactive and cloud-native and Kotlin and all sorts of good stuff. But I do want to talk about something that just happened 2 days ago first. I want to talk about something that happened 2 days ago that I think is just super-duper cool that I just want to show you, okay? Have you heard of this thing called Spring Foo? Spring Foo, F-U. It's a new project that we just found. It's like an experiment. It's a test bed for new examples, new ideas, and we'll see what happens with this project. We'll see if some of the ideas germinate and become part of Spring Boot, for example. And there's some interesting applications here. I think the goal ultimately is to have a Kotlin first approach to building services, right? The idea is to support these Kotlin-based applications and to provide a micro framework. And so, as part of that, we also want to support functional programming, right? We want to support functional programming, and to make this a sort of an integrated, native part of the story. And so, as part of that, we have taken a very simplified approach to building the core of this engine. We've essentially used a new feature in Spring Framework 5 called functional bean definitions, right? Not Java config, but functional bean definitions. And when you do this, you get some pretty amazing results. So let's just take a quick look at that. I just want to show you this before we get started, because I think this is super cool. So I will go here to my desktop, and you can see here, Spring Foo, good. All right, and I'm going to go to my my sample here, samples, minimal web app, okay, and we're going to say idea build.gradle.kts. Just going to open this up. This is an existing example. This is only possible as of like a day and a half ago, less than 48 hours ago. This became possible, and I think it's something I just want to show you because it's just one of those cool things that you should see. So this project, again, very, very simple approach. It assumes Kotlin. So I'm going to show you this sample here. Wait for IntelliJ to realize what's happening. Application. There we are. So there's my simple micro example. Okay, very, very simple example. It's using Kotlin, and that's it. That's the whole application. It's an application. It has Spring WebFlux. WebFlux is the reactive web runtime. We'll talk about that in a bit. It has a server. The server is based on Netty, and it supports HTTP routes and so on. And you can do all sorts of other, it's a full framework, so you can create, it's Spring after all, so you can create beans of type foo, for example. I can say I want to register a bean, or I can actually just register a bean itself like this, using the bean callback application, initializing bean, there you go. So all sorts of interesting things there, okay? That said, it's really fast, right? It's very, very fast. So let's try this. Let's go ahead and just run it and see what happens. Let it compile the first time. All right. So there's the application. And it started very slowly. You see, it started very slowly in this example. It took 1 second. Let's try again. There. So that's 838 milliseconds, which isn't bad, right? Not bad at all for a web server and a reactive web application and all of Spring and all that stuff. But we found a way finally to make this go much faster. So how many of you know about GraalVM? Oh yeah, good stuff. So GraalVM it's just source. It's like witchcraft. It's amazing, right? There's this. It has the possibility of being an amazing way to compile and work with JVM artifacts without using the JDK, and you get some awesome secondary benefits, which is I'm sure have you seen Oleg's talk? Did you do a talk on it? Yeah. So watch his talk. Just watch that. But suffice it to say, one of the most amazing features of many in this toolkit is the ability to compile your code and create a native image. And basically, it co-locates the virtual machine. It co-locates the everything you need to run the application, a garbage collector, all that kind of stuff inside of one image. And that image has everything that the application needs already sort of arranged in such a way that it can just be loaded into memory directly. There's not a lot of like messing around when the application starts up. So let's go ahead and compile this application using the native image builder. So I'm going to use this script here. And this is, by the way, in GitHub. This is under the Spring-Foo Git repository, and then you can find the samples. In order to make this work, we need to say export Java home equals home JLong Josh bin GraalVM. Okay, and then export path equals path and Java home / bin, right? So there we are. There's our updated path, including the Java home bin directory. And now we can run this program. Now, I'm not sure if you can hear that. Can you hear that? That's the sound of my fans, of the fans on my computer losing their mind. This poor machine is suffering. It wants help. And that is not Slack, by the way, right? I'm not running Slack. That's not Slack. It sounds very similar to Slack, but it's not. It's doing some, I don't even know what it's doing. It's just doing some amazing things behind the scenes. Can you hear that? I have 32 gigs of RAM and a Xeon server, and my computer just got confused and very sad for a minute. Okay, wait for it. Wait for it. So it's almost there. I hope that's not Slack. I think I shut Slack down. All right, good. Still, okay, good. So now, what that gives me is this file here, this right here, org spring framework, blah, 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 okay? And that file is 46 megabytes. That has everything I need to run this application, including the runtime, basically. And that's cool, okay? Now, what I'm going to do is I'm going to start this program up, okay? Now, I want you to count in Polish to 3, okay? So, yeah? Okay, we're done. That was 2 milliseconds. There's the running application, thanks to GraalVM, up and running in 2 milliseconds. So that's really cool. What do you think of that? I mean, that's you know, the application runs the same as it normally does. It's a it's a basic application. Everything you can do lots of things with this approach, but I think Graal gives it an extra kick that you can't really get otherwise. And so I just wanted to share that with you. That wasn't possible. We've been working with the Graal team and working with other people, and finally, about like less than 48 hours ago, we figured out how to get this all to work, and I just think that's super cool. So, okay, anyway, that is Spring Foo, and I hope you'll try it out, give it a shot. That's not really what I wanted to talk to you about today, but I just thought it was super cool. Now, my friends, we have very little time together today. We have very little time. We have like 2 hours, right? So you should have hopefully seen on the schedule that there's actually 2 talks. There's this talk and the next one, and you can consider them as just one long, big talk. And we're going to talk about all sorts of things today, all the latest and greatest. And because of that, I want to remind you that there's Git. There's a source code repository where you can find all the information about, you can find all the code so you can follow along at home. And as always, if you have questions, if you have comments, if you have feedback, whatever, don't hesitate to reach out to me. I'm happy to help. I'm happy to hear from you. I'm at your service. So how many of you, I'm just curious, are on Twitter? Just curious, Twitter. Okay, very good, Twitter. All right. What about the rest of you? Get on it. What are you doing? It's 2018. Get on Twitter. It's the new IRC. It's a great place to be. It's where the developers that drive the open source that powers your businesses are. So you should be there. And if you ever have questions, don't hesitate to reach out to me on Twitter. What about email? How many of you have email? Email. Anybody? Anybody? No. Good. Moving on. Good. So, a little bit about myself. My name is Josh Long. I'm a Spring developer advocate. I'm an open source engineer. I do these weekly videos well, there's seasons, right? There's like different seasons. There's been 4 seasons so far, but every Wednesday, there's a new video that looks at some corner of the ecosystem. These are on YouTube, and if you want to find the playlist, you can go to bit.ly/spring-tips-playlist, and you'll find those videos. I'm a Java champion. I'm an open source contributor and engineer. I have the dubious distinction, the questionable distinction of, in my time as a contributor to the various Spring projects over the last 10 plus years, I have the dubious distinction of being the number one, top-ranked, most highly lauded, most visible, most highly acclaimed contributor of bugs, but still number one to all the projects to which I've been a contributor, including Spring Boot, Spring Cloud, Spring Integration, Spring Batch, Vaadin, Time Leaf Activity, etc. So there's that. And I do these training videos. These are on Safari. These are on an online marketplace for technical content. You can find all sorts of good stuff there if you like. And of course, I finished. Last time I was here, this was not finished, but I finished my 5th book. This book is called Cloud Native Java. And this book is all about how to build applications that survive and thrive in the cloud using Spring Boot, Spring Cloud, and Cloud Foundry. Now, this book is something about which I'm very proud. I'm very proud of this book, but it did take, in point of fact, it did take a little longer than I had expected it might take. I was expecting that, given what we know, what my co-author Kenny Bastani and I know about the ecosystem, about the technologies in place, I thought, given what we know, that this would be an easy thing to get done within 6 months, no problem. But it did actually take a little bit longer than we expected. It did take just a little longer, a little bit. Now again, there's lots of reasons for this delay. There could be a lot of reasons for this delay, but I don't want to point fingers or anything like that. It's definitely not O'Reilly's fault. I don't know why you would say that. Why would you think that? That's crazy. I mean, no. But also kind of maybe a little bit. It did take, because like I said, it took a little longer than we thought it would. We expected it to be just 6 months, and we thought, okay, sure, very ambitious. Very ambitious. We've got Spring Boot, we've got Spring Cloud, we've got Cloud Foundry. These things change all the time. They change all the time. But we thought we could do this, 6 months, no problem. It did take, as I say, it just a little. It took 2 years. All right. It took 2 years longer. Okay. It took 2 years to get it. But there's a good reason for that. You see, there were sometimes cantankerous, sometimes very intense, sometimes very rancorous, sometimes very arduous, sometimes very heated debate that went on between us, the author team, and our publisher O'Reilly. And again, the back and forth, I think in the end, proved the results. But we did, as I say, it did take a little longer than we had expected. You see, we spent 18 plus months deciding on the animal for the cover. Now, anybody who knows anything about O'Reilly books knows that it doesn't matter what's in the book itself. Nobody cares. It's everything to do with the animal on the cover. And we eventually settled upon a blue-eared kingfisher. This is a bird that is indigenous, or as we'd say in English, native to the Indonesian Java Islands. It's a bird that is native to the Java Islands, and birds fly, yes, through the clouds. So it's a cloud-native Java bird. It's a bird. Never mind, it'll come. Never mind. It's okay. It's okay. You'll catch. So there's that. And of course, I work at Pivotal. And at Pivotal, we have a lot of great open source software. We care about open source software always. But as I always like to remind people, this is not the reason we're here. It's not the thing that most motivates us. In fact, it's not the reason that any of us should be here. What we care about at Pivotal, more than anything else, and by the way, Hi. Very cool. Oh, yeah. Look at that. So cool. Thank you. So it's not the reason we're here. It's not the thing that most motivates us. What we care about first and foremost is helping people build better software. We want to help them move software from concept to customer as quickly and capably as possible. And we know that a lot of organizations struggle with this. They know that they need to go faster, but they don't know how to go faster. They look around in the ecosystem. They look at these other companies and they say, well, that company's going quickly. How are they able to do that? And what is their secret to success? Well, these organizations are able to go quickly, for a lot of reasons, and it's misguided. It's misguided to say this organization is able to go quickly because it's a small organization. You can look at these startups. These startups are able to go quickly. Is the reason that they're so successful sometimes because of their size? I think that's close, but it's not quite right. It's missing a very important point. You see, it ignores the reality of much larger organizations. Much larger organizations like Amazon, like Netflix, like Google, like Twitter, like all these other companies that are able to innovate much, much more quickly than even the smallest of startups. So what is the secret? Well, I think it has to do with not with the size of the organization, but with the size of the teams working on the code. Right? The smaller the team, the easier it is for that team to work on the code independent of other parts of the organization. The less the cost of communication across different teams in the organization, the more readily that these teams can deploy new features. This is not a new idea, right? This is not a new insight. They've done lots of different studies where they confirm this effect. They looked at, well, first of all, you've all heard about Mel Conway and Conway's Law, right? In the 1970s, Mel Conway had this insight. He said, well, software is a mirror image of the communication patterns of the organization that built it. Put another way, if you have a dysfunctional organization, you will produce dysfunctional software. Put another way, crap in, crap out. Right? And they've done a lot of different studies to confirm this effect. They looked at different teams. They had one example I see is if you have 4 different teams working on a compiler, you'll get a 4-pass compiler. Right? 4 passes in the compiler. It's just natural. The software reflects the structure of the organization, and it reflects the dysfunction of that organization. And they did studies to confirm this effect. They looked at open source software, and they compared it to proprietary software. They looked at something in the open source world, and they compared it to something exactly like in the proprietary world. Imagine you had the opportunity, I'm using big, really sarcastic air quotes. Imagine you had the opportunity to look at the source code for Microsoft Office. Opportunity. Imagine that you had this opportunity to look at that source code. What do you imagine you would see? What do you think you would see if you were to stare into the void of that code base? What do you think would stare back at you? Would you blink? Or would it blink? I've never seen that source code. I'm still alive. Obviously, I've never seen it. But, hypothetically, what you would see hypothetically if you were to stare at that source code and then compare it to something of similar form and function in the open source world, something like OpenOffice, for example. What you'd see is that the open source code tends to be far more modular than the proprietary code. And this has nothing to do with the technical acumen of the engineers. It doesn't have to do with how skilled an engineer these people are. There's no correlation at all. Think about the contribution model for people working in open source. People working in open source, they're in different parts of the world. They sit in different offices. They sit in different places. They speak different human languages. They are contributing at different cadences, right? Different opportunities. Some people contribute in the early morning. Some people, before they send the kids to school. Some people in the evening after work. Some people on the weekends or not at all for weeks at a time. And then they do a lot of work and then they disappear. For these people working in open source, the opportunity to contribute code is rare. It's not as often as people working in proprietary. And imagine you're working in a proprietary code base. You're all in the same place, working for a big company maybe. You're all in the same office. You speak the same human language. You're all talking and working roughly the same hours, 8 to 9, 8 to 5, or 9 to 6, or whatever your agreed upon hours are. And if there's a change, if you want to make a change in the code, and you're working in a proprietary code base, you just turn your chair and say, Jane, I have an idea. What do you think of this? And Jane and I can have a very quick discussion. Jane knows all about this part of the code. We can have a quick discussion. She can help me implement that feature, right? The cost of coordination is very little in this case. Whereas with open source, well, the cost is very high. If I'm in California in the United States in PST, and I want to work with somebody in Southeast Asia, well, somebody's going to have to wake up very early or go to bed very late. Is that true or not? It's going to be a very difficult process to get on the same page, to have a discussion. So for these people, the cost of coordination is expensive. To reduce this coordination cost, we need to make it so that people working in code can work on just the thing that they care about and move independently of other parts of the team, of other parts of the organization. They need autonomy. They need the ability to go faster. So how do you do this? Well, you break your large code base into smaller chunks, small batches, small, singly focused, independently deployable, reusable, bounded contexts. If you can do this, what you have is a microservice, right? A microservice is a small, singly focused, independently deployable, reusable, bounded context. It allows you to focus on the thing that you care about, and as long as you have a stable surface area component boundary, then other parts of the organization don't need to coordinate with you, right? The cost of communication is limited to just that contract there. It allows you to go faster. Now, when you move to this architecture, you have a lot of benefits, of course. Technical benefits are secondary. The first benefit is agility. There are some technical benefits. It becomes easier to reason about the scope of an impact of a change. It becomes easier to scale out individual pieces of the software. It becomes easier to test pieces of the software. It becomes easier to do a lot of things when you move to this architecture. But you also run into some problems as well. I call these the hemorrhoids of cloud computing. Do you know what a hemorrhoid is, my friends? It's a real pain in the You're going to face two of these. The first one is, how quickly can you stand up a single production-worthy service? How quickly can you address all the non-functional requirements required to build a production-worthy service? Imagine you wanted to build a service that just did hello world right now. You wanted to deploy it into production. How quickly could you do this? Into production, not just staging, but I mean into production. What would you have to do? Most organizations that I speak to, surely not yours, of course, not yours, but most organizations that I speak to have the dreaded wiki page with 500 easy steps to production. This wiki page is the list of non-functional requirements that you need to do before you can deliver line 1 of business differentiating functionality. And you need to do all of this, right? The goal here is to go faster, but you cannot compromise and give up reliability and safety and all these other concerns. You can't skip a step. This is why you have to embrace a holistic approach here. Microservices are part of a larger story around continuous delivery. We can embrace things like test-driven development, continuous integration, cloud computing, microservices, TDD. All these things are based on getting a faster feedback loop. And when you move to this architecture, you have to be able to automate away all these real concerns, things like security and observability and monitoring and load balancing and racked and stacked servers and infrastructure and SSL and security patches and all that stuff. How quickly can you get rid of all that? Well, that's the first thing. And these days, when I talk to organizations, I talk to them about things like Cloud Foundry, which is a great way to run applications in production. I talk to them about Spring Boot, which is a great way to build production-worthy applications. And I think that's a fairly easy message to understand, right? These things are technologies that allow me to focus on the thing that I care about, which is my business logic, and let the automation take care of the rest. Then you run into the second problem, the second hemorrhoid. Once you've done this, once you have managed to deploy lots of services into a production environment, well, now you have this proliferation. You have this proliferation of services. You have lots of small services talking to each other over the network, right? And when you do this, you invite new complexity. You have lots of services that talk to each other. That communication means that you have a distributed system. When you build a distributed system, you invite complexity that you need to address. And you run into some problems that aren't visible when you have a single node. They're not obvious when you have a single node. Things like latency, right? We run into a situation where we start to realize that as we add more input and output, as we start to do more input and output across the network, as we start to move more data from one node to another across the network, we start to saturate our input and output buffers. And we start to appreciate that the traditional approach to solving this problem, to doing input and output on the JVM, while it has served us well for a long time, isn't particularly efficient. It's not particularly scalable. To illustrate what I mean, let's think about how a traditional web server works. You have a server socket. The server socket sits there, and requests come in. As the request arrives, your web server creates a thread. That thread is responsible for producing a response. It wakes up the servlet engine in your server. The servlet engine wakes up your servlet, the Spring MVC dispatcher servlet. The Spring MVC dispatcher servlet wakes up your controller or REST controller. And then your controller activates the handler function, the handler method. All of this happens inside of that thread. And the request comes in, your handler method gets invoked, and the response gets sent back, all inside the same thread. And as long as the time it takes to do this is very small, as long as it's very short, then you have no problems, right? It takes no time at all to do that. If it does take a long time to do that, though, then you have a problem, because you have a very limited number of threads in the operating system. The cost of threads on the operating system is very high. And even if you could create 1 million threads, you still have the problems of contention, thrashing, coordination. So you have to mitigate that as much as possible, minimize it as much as possible. So we have a bottleneck here. We can't have threads as a means for scalability. And you shouldn't have this anyway. You see, it is not a requirement that input be connected to threads, or input and output be connected to threads. There has been in your operating system for many years support in the operating system for decoupling the management of I/O from the use of threads, right? Most operating systems have at the lowest level a way to say, here, operating system, here's some file descriptors. These file descriptors have bytes in them. They have data. When there is new data, let me know. Call my code back. It's a callback. So the operating system manages the input and output, and if there's anything I need to process, then I get notified. This is very different from the way we normally think about input and output on the JVM. If you've ever used Java I/O input stream and Java I/O output stream, you are more used to thinking about it in a very sort of pull-based fashion. You're pulling data out of the input stream. When you have an input stream, you read one byte buffer at a time until the byte that you read is -1, right? That's pulling data out of the input stream. In this new model, the operating system pushes the data to you, right? And so you get notified when the data is available. Now, if you are supporting this approach, and you are working in this asynchronous approach, well, you need something that you need to be able to use tools above that layer in order to make this work, right? We can't use things that don't lend themselves, that are not compatible with this approach. All these years, we've used Spring, right? We've got Spring and Hibernate and these tools that have served us well for so long. Imagine that for some reason, for whatever reason, Spring and Hibernate just really hated Java util collections, right? Java util collection, Java util set, Java util list, all these types that we know and love. Imagine if Spring and Hibernate and all these other frameworks that you've used did not know about them. They were hostile to them. They were allergic to them, right? Imagine that if you used a Java util collection in Hibernate, imagine it didn't just throw an exception. It actually rendered an ASCII art middle finger, right? And then segfaulted your machine. Would you use Java util collection types with Hibernate if you knew that was going to happen? Of course not, right? You'd make sure to never use these types again because they will just cause you no end of trouble. You'd say, I will do something else. I need to get data from the database. Hibernate is a great tool. I'll use whatever they recommend. I'm not going to use Java util collection. Same thing for Spring, right? So we use these tools because they support the types that we want to work with, and we model things in a certain way because they work with these tools. The same is true here. If we have a way to work with asynchronous I/O, if we have a computational metaphor, a type that we can use to model asynchronous amounts of data, asynchronous data that is potentially unlimited, right? If we have such a metaphor, then the things that we use on top of that have to support that type, those types. So we need some way to model this kind of data. We need some kind of thing that supports this kind of asynchronous amount of data, and it needs to be supported at higher levels. Think about what we're trying to do here. Again, if a request comes into the web server, and the request that hits the web server is produced as quickly as possible, then you don't need to worry about reactive programming. If the time it takes for you to produce a response is less than the time it takes for another request to arrive at the web server, then you're fine. Don't use reactive programming. But if the time it takes for you to produce a response is more than the time it takes for another request to arrive, and thus you get into a situation where you have no more threads, well, you need to find some way to shorten that time, to move the work and free those threads up. That's what reactive programming is all about. And we need some sort of computational type, some sort of API that lets us describe the world in this way. So for this, we can use the reactive stream specification. The reactive stream specification it's a set of APIs, a set of types that comes from the Reactor project, or from the work being done in part by RxJava, by Pivotal, by Red Hat, by the Eclipse Foundation, by Netflix, etc. These types are what give us what we need to be able to support what we're trying to do. And on top of that, we must have support for doing data access, for doing security, for doing web programming, and so on. So that's what we're going to talk about today, my friends. We're going to talk about the journey that started last September, just a few months after I was here last time. Last September, we released Spring Framework 5. And then after that, we released Spring Data K for reactive data access. And then after that, we released Spring Security 5. And then after that, we released Spring Boot 2.0 in March of this year. And then after that, we released Spring Cloud Finchley 3 days ago. Right? So this is a journey from before to now, where we have GA releases of all the different key Spring projects here that support reactive programming. So we're going to build services today, as always, by going to my second favorite place on the internet, start.spring.io. Now, let's see. Close this. Downloads. So we're going to go here to start.spring.io, and we're going to build a new application. And this application is going to be a service that we're going to build that uses these reactive types. We're going to call this the reservation-service, just like I always do. And we're going to call this we're going to use the config client. We're going to use Eureka for service registration and discovery. We're going to use Zipkin for distributed tracing. We're going to use the reactive web support. We're going to use the reactive Spring Cloud Stream support. We're going to use the reactive. We're going to use Kafka as our binder choice here. Kafka. And we need some sort of persistence option. We also want to use Lombok to make Java just a little bit less tedious. And then we need some sort of persistence option. And there are a lot of different choices here, so I'm going to switch to the full version. When we look at this full version, we were given a list of checkboxes, things that we could add to our application if we wanted to. But when we first scroll down, we see this list of SQL options. These options are not for us. Not for us. What we're trying to do is to support reactive programming, and at the moment, these SQL options are built on JDBC, which for the moment, maybe that'll change in our lifetime. For the moment, these are synchronous and blocking APIs. You cannot use them in a reactive way. In order to scale out your use of these APIs, you need to scale out with more threads. So we want to avoid that. So instead, we must confine ourselves to the list of NoSQL options. And only a few of them support natively reactive code. Now, there's a number of good choices here. We could use Reactive Couchbase or Reactive Cassandra, both of which are good choices, but I don't have those on my machine. We could use Reactive Redis, and we will come back to Reactive Redis later on. We'll talk about Reactive Redis in a little bit. But instead, we're going to focus on Reactive MongoDB. Because when you want to lose your data, and you want to lose it reactively, there is nothing better than Reactive MongoDB. Now, I'm happy with these choices, and I kid, by the way. I like Mongo. It works fine. It's got a lot of features. I'm, just teasing. But we're gonna use the default choices as they were selected here. I'm happy with these choices. That said, quick question actually. That said, do you want to do this in Java or Kotlin? Who doesn't want to see Kotlin? Oh, that's a fair amount. How about we do half-half? Can I do this one in Java and then the next one we'll do in Kotlin? Is that fair? Let's just do a half-half. So I'll do this in Java, but I promise that the next service, the next big service we'll do in Kotlin, then you'll get to see a little bit of both. Okay? These selections, as I've made them here, they're fine, right? They're default choices, lots of good options. I encourage you to take a look at these drop-down menus later on. They imply a choice where there is no choice. There's no choice, right? There's the choice of Java version. What version of Java would you like to use in middle of 2018? You have two choices, but they're not really a choice, right? Remember, Java is now on a 6-month release cycle. So if you use 10, you have to upgrade as soon as 11 comes out in September or October. I forget when, one of those months. Right? It's on a very short release cycle. And if you get to 11, 11 will be a long-term release, so you can stay there. So for now, I would recommend that you stay at 8. That's a good choice. And then when you get to 11, then you can upgrade to that. Then we have the choice of packaging. People are often confused by this. They don't know when and where to choose which. So I'll do my level-headed best to explain here and now. Yeah. What's happened? There we are. Okay. I'll do my level-headed best to explain when and where to choose which here and now. If, by some fluke of physics, some terrible tragedy of time-space, some awful accident of history, you find yourself somehow transported to the distant, distant, distant past. Far, 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 far beyond modern help. Then choose .war. But if you're here with me in 2018, then choose .jar. This is a big part of my overarching and guiding personal philosophy of make jar, not war. I hit generate, and that gave us a zip file. I'm going to open this up in my IDE. I'm going to use IntelliJ. Anything that supports Java 8 in this case, or better, and Maven in this case, will work just fine. NetBeans is a good choice. Eclipse and Spring Tool Suite are good choices. IntelliJ, Community, or Ultimate are good choices. I mean, anything will work just fine. And once I've done this, I'm going to go ahead and comment out some of the dependencies that I don't need just yet. Okay, so I'm going to go down here and comment out the Spring Cloud support here for Kafka and Zipkin and Netflix Eureka and the config client, and there we go. Goodbye. So now we're going to build a new application, and we're going to save this application. We're going to save the data into the database, like so. We're going to create an entity of type reservation, and it's going to be an entity that we're going to store in the database using @document. We're going to have a field here, private string ID and private string reservation name, and the ID. We're going to store in the database. We're going to tell the database to treat that as a surrogate primary key sort of thing. Now, this is Java, so I need to create getters and setters and accessors and toString and equals and all that stuff. So instead of doing that myself manually, I'm going to add in some Lombok to make it just a little bit less painful. Okay, so @noargs, here we are. Okay. Now, I'm going to save some data into the database. So I'll create a Spring Data repository, as I always do. But this time, I'm going to use reactive Spring Data support here, right? So reservation, string, etc. And this repository should look very familiar. It supports all the sort of things you might expect before, from creating, reading, updating, and deleting, and so on. But it has publishers. It takes a publisher as its input. And a publisher is a reactive streams type. A publisher emits items. It publishes items. The subscriber then receives those items in the on-next callback. When the subscriber subscribes to the publisher, it is given a subscription. The subscription is the link, it's the session between the producer and the consumer of data. When the subscription gets notified, it then asks for more records. It says, I want to request 10 records or 1,000,000 records or 1,000 records, whatever. That is the subscriber's opportunity to signal to the producer how much data it wants. It's how you achieve flow control. When you build a networking protocol, you have to think about flow control. In the world of reactive programming, when we talk about flow control, we also say back pressure, right? That's the marketing word for flow control. A very simple idea. So these are the three most important types. There's a fourth type that you have to care about called a processor. And the processor is just a reactive streams type that is both a subscriber and a publisher. It's a producer and a consumer. It's a bridge. It's a source and a sink. And that's it. You understand all of the reactive streams types and how they work. And that means that we can write write code that produce publishers. But when you look at this code, there's actually two other types that we need to be aware of. There's mono and flux. Mono is a publisher that publishes 0 or 1 record. It's kind of like a future, but it supports publisher semantics. Then we have a flux. A flux is a publisher that produces 0 to n records. 0 to potentially unlimited records. This is an important understanding. Remember, reactive data, large amounts of data, might be unlimited, right? This is data that may be latent. It may be eventual. It may be, essentially or eventually consistent, right? This is not data that's here right now. It might be here in a nanosecond. It might be here in an hour. It might be here in a week. So we need to be able to say, I have a large amount of data. We don't know how much. For example, with WebSockets, how do you describe that, right? So this gives us a way to say, I have unlimited amounts of data. It's not all here right now. Now, I want to write data to the database. So we're going to write some data to the database using a data writer. It's going to implement application runner. And the application runner callback interface is what we're going to use to tell Spring to write data to the database when the application starts up. So we're going to say that we want to inject our reservation repository like so. And we're then going to write some data to the database. I'm going to use some names here. I've got my friend Marcin and my other friend Jacob, and there's me as well, and who else? Sorry? How do you spell it, my friend? What is it? Spell it? N-A-R? What? Let's just say Bob. I'm sorry. We don't have time. I'm sorry. Okay, so string, names. All right, so there's our names. And now we're going to go to each one. We're going to say for each name, I want to turn it into a new reservation, like so. Okay, reservation, pass in null. And then I'll say name. And that's going to give me a publisher of names. Look at that, a publisher of names, a publisher of reservations, rather. So we have now reservations. And now I want to turn each one of those, and I'm going to map it. I'm going to take each reservation and say reservation name. Okay, so I'm going to map it into, I'm going to turn that into a saved reservation. So what I'm going to say save that to the database. Whoa. This.rr.save, passing in R. All right, good. And what happens if I call save? Save gives me a mono of T. I get a publisher of publishers. Can you see that? Yeah, barely. It's a publisher that gets returned from save. So when you use the map operator, what happens is you end up accumulating the output of this lambda. Well, the output of this lambda is a mono of T. So you have a publisher of publishers of T. So this is actually a publisher of reservation. Well, I don't want a publisher of publishers, right? I want just a publisher of reservations, not both. So I can use flat map instead. Flat map like this. And I get rid of that. There we go. Now, what happens if I run this code? Right now, if I leave this code as is, what's going to happen? Nothing. You see, this code, like me, is lazy. It needs to be encouraged to do work. And so you can do this with a subscribe, right? You say, I'm going to subscribe. You can provide a new subscriber from the Reactive Streams API, a subscriber, or you can use the overloaded versions that we have in Reactor, our API, our overloaded version. And you can do things like system out print line, right? And that's certainly fine. And this is actually a publisher. When I say publisher, it's also a flux, so I can get rid of that intermediate type there. So that will work. But there's also another problem with this code. You see, this code is going to execute, but it reminds me of an old saying in English that a broken clock strikes true twice a day. Have you heard this before? What it means is that if you have a clock, like an analog clock, not digital, and the hands are stuck, they're not moving. It means that in the morning, in the AM, that clock is correct, at least one instant. And then in the evening, in the afternoon, that clock is also correct again for one instant, right? So 2 times a day, it's still correct. And the same is true for MongoDB. It will save your data at least twice, every now and then. Not all the time, not even close, but enough. So we need to be wary of that fact. We need to know that it will, we may have collisions. I don't want to have duplicate data. So I'm going to delete this data first. I'm going to say this.reservation repository .delete all. And when I do that, I get a mono. So I could say, okay, subscribe again. That's fine. But what happens with this code? If I run this code, I've got another problem. This code is asynchronous. There's no guarantee that this code will execute on the same line as this one. So I need to force this line to execute before the next one. And I can use the operators in Spring and in Reactor to make this code a little bit more seamless. So let's get rid of these intermediate variables because we don't need them. And then rewrite the code to support what we're trying to do here. All right. So that is the rewritten code. And what I'm doing is I'm saying delete everything, then do this, then do that, and then subscribe finally. Okay? Now I like this result. Let's go ahead and see what happens if we run this code. If we run this code, we see our names, or we see some names down there. There's the 4 names. It worked. Of course it worked. It was a demo. Instead, what I wanted to focus on was this. This is the ASCII artwork in Spring Boot. This ASCII artwork took a long time to get right, but we on the Spring team have many people who are doctors, PhDs, people in their previous lives worked in nuclear physics. So it makes me very happy to imagine that someday, somewhere, somehow, there's a GitHub issue that said, darn it, we need good ASCII artwork. And I think you'll agree, they did a great job. So it's for this reason that I want to take just a brief moment, and a very brief moment, to talk about what I consider to be a glaring and serious deficiency in the IntelliJ JetBrains product. Because even though I am a fan, I consider this to be a particularly bad bug. Do you see that checkbox? That checkbox, once clicked, suppresses the output of the ASCII artwork. What the hell? Why is that there? That's a dumb feature. So I did what all people would do. I went on the internet and I cried. I'm not a hero. You don't have to thank me. And my friend Jan Sabran, this is my friend Jan Sabran, he's a software developer by passion at IntelliJ JetBrains. And he responded with this message of hope, which I share with you here today. He says that'll be in the next release, for sure. He keeps saying that. I mean, this was 2016. So, maybe it's not. Maybe it's coming next time. I don't know. Anyway, some people ask me, can I change the ASCII artwork? And yes, you can. It's a ridiculous question, though. You're not going to do a better job. Just know your role. Know your limitations. But still, if you feel like you could do a better job, let me show you how. Source. Downloads, reservation service, source, main, resources. Now I go to the reservation service, Maven clean. Let me kill this application here. Okay. Spring-boot, :run. Awesome. Not bad at all. Now, that's an old trick. We could do that before. We're here to talk about the new latest and greatest stuff in Spring and Spring Boot. So let me show you the latest and greatest, arguably the most important thing that's ever happened to software ever. So I'll get rid of that. Copy, desktop, misc, banner dot, aha. Yeah, sure. It adds like 30 seconds to the startup time. I don't even care. Totally worth it. Amazing. If you had any doubts about upgrading to Spring Boot 2.0, that should put those doubts to bed. You should be ready to upgrade right now. Now, that said, we don't have a lot of time, so I don't want to waste that. So I'll go ahead and get rid of the banner.gif for now. Okay, and get rid of the target. But you should absolutely be upgrading yesterday. Okay? Now, we have this data, we have this database, we have data in the database, we have amazing ASCII artwork. Let's build a REST controller. So at REST controller, class, reservation, REST controller. And we're going to create an endpoint like this, reservations of reservation. I'm going to say this.reservation, we're going to inject the reservation repository. So I'm going to say private reservation repository RR, add constructor arguments, and say return this.rr.findAll. Very good. Okay? So go ahead and start that up, and that'll give us a regular REST endpoint that works very similar to what we have seen before if you've ever used Spring MVC. And it looks like Spring MVC, right? Obviously, it's very similar. It even uses the same annotations. There's the data. It has the same annotations, but this is not Spring MVC, and this is not the Servlet API. This is Spring Webflux, and that is Netty, right? There's no Servlet API at all here. And we're doing something here totally different than in Spring MVC. We're returning a publisher. There is no place in this code where we collect all the data in memory and then turn it into JSON or XML or anything else like that, right? We are streaming the data and turning it into whatever content type is required as the data is being published. Because otherwise we would overflow our buffers. We'd have, we could have like unlimited data. We can't wait for the end of that and turn it over to Dom or Jackson to Marshall. We need to manage that as we see the data. So this is a completely different framework, even though it looks very similar. And you can do a lot of similar things, obviously, but it is not the same thing. Now, that said, there's a different style of endpoint in Spring Framework 5 called the functional reactive endpoints. And the way it works is you say router functions dot route request predicates dot get / reservations new handler function, etc. So here, I'm going to say server response.ok.body, and I'm going to inject the reservation repository, rr.findAll, and I'm going to say we're going to return a publisher of reservations. Now, that looks a little long in the tooth, doesn't it? There's a lot of ceremony there. Let's clean that up a little bit. Alrighty. Good. Okay, so there's our updated code. So there we go, up and running. Here we go, same API. Now, which one do you use? When do you use which? Well, it's up to you, right? Two different styles. You can use both of them in the same application. I like this style for a couple of reasons. First of all, it's very succinct, very, very short. Also, it's more programmable in that this first parameter is a request predicate. I'm using a request predicate DSL, but you could provide your own request predicate, and you get full control over how the matching of incoming requests looks, like this, right? So if you want to do that, you can. Or you can even chain them together. You can say get.and new request predicate. Return math.random greater than 0.5, for example. So you now have full control. Whereas if you're using Spring MVC or Spring Webflux with the annotations, this annotation here is it's based on what Spring Framework can do. If you want to change the default behavior, then you have to go below the annotation component model. Whereas with this, it's just top level. So I like that. And then the other thing is that it's just also very, very succinct. You have all of the endpoints in the same place in the code. So it makes it easy to figure out what's happening, right? We have a server request. We can look at all the routes. We can use lambdas if you want. You can use method references. You know, mix and match. Now, we have an application. It's up and running. We're in a good place to now talk about what happens if you have a Spring Boot application and you want to deal with this in production. You want to scale it out. Now we can talk about those distributed systems concerns, okay? So, a few things. First of all, I want to keep my configuration not in this config file here. I could use configuration in Spring Boot. I could do that, for example. I could do that, but I want to keep my configuration outside of the application. So I'll use a Spring Cloud config server. Now, you could create one easily by going to the start.spring.io, but I'm just going to go ahead and start one up. I'm going to use a directory full of configuration. This is my Git repository, full of configuration, full of property files. I'm going to git clone this into my local directory here, my local machine, desktop config. Oh, sorry, I've already got one, so desktop config. Okay. And with that done, I'm going to create a config server that will run and manage access to that directory full of configuration for me. And that will be up on port 8888, and other microservices will identify themselves. They'll say, my name is, oh, it's downloading the world. Awkward. Huh? I really need to update this all to Finchley. It's using very old versions of Spring Boot. It's using Spring Boot 2.01, not 2.03. That's like, you know, forever ago. So now, I have this config file, and this config server and other microservices will go to the config server, and they will identify themselves. They'll say, my name is the reservation service, and they'll get sets of configuration, keys and values from different property files. I have a message here that says, hello, Singapore. I haven't been in Singapore for more than a week. I have been in 6 other countries since then. That is a wrong message. It's wrong. We need to change it, okay? We also have this port. Port equals 8000. Well, so I want to change my microservice. I want to change my microservice to use the Spring Cloud config server. Bring that in. Good. And with that in place, I just need to give my microservice a name. Spring application name equals reservation-service. And I also want to use this message that you see in the config server here. Hello, Singapore. So we go there and route, whoa, message, R, OK, body. And we're going to inject the environment, the Spring Framework environment here. Never this one. Don't ever choose that one. That's dangerous. You won't like the result, I promise. env, okay? So it's going to be a flux.just env.getProperty message. And we're going to create a publisher of type string. There we are. By the way, did you notice how I can chain these endpoints together? Right? That's the nice thing about this, is that we have a DSL for functionally registering REST endpoints. So I can do interesting things. I can say, okay, well, let's store this as a variable, right? And I can do here. I can say route equals. There you go. That's as an example. I can say if math.random is greater than 0.5, then I want to have this REST endpoint, right? Or something like that. I can do a for loop, right? I can create custom REST endpoints based on a for loop or any other kind of logic that I want. So all sorts of interesting options there. But anyway, going past that. Okay, get rid of this. There we are. Now, I have my REST endpoint, my REST controller. Let's spin this up and see what happens. It's going to draw its configuration from the config server. I want to be able to use the config server to get my configuration, and we should see that the application starts up in port 8000. There's the message. Here's the reservations. That's working. So good. So now what I want to do is I want to change that message. That message is in the config server. I can use Actuator. Actuator are it's a framework that provides a set of observable endpoints here. For example, Spring Boot starter Actuator. Do I have that in the class path? I need to add this. So I say Spring Boot starter Actuator, and then restart. And the actuator provides a set of observable endpoints that I can use to look at the state of the application. I can see, for example, that the actuator is here. Actuator. Oh, in order for me to use it, though, what is that? Failed to handle request. Okay. There's the actuator. It provides a number of different endpoints that show me things like my health, you know, the beans, the audit events, config props, info, loggers, all this kind of very interesting stuff that we care about. What we want to use is the refresh endpoint. So I'm going to use the refresh endpoint to change the configuration server values live. So I'll go to the desktop here, config, Emacs, the reservation service.properties, hello, Krakow, right? Whoop. Is that like, what is it? Krakow? There you go. Extra, exclamation marks. Git commit -a -m, YOLO. Now, I'm going to send an empty HTTP post to the actuator refresh endpoint. -h, content-type, application, JSON. Okay? Ready? Go. Whoops. Where'd it go? Sad. Okay, let's try that again. There's hello Krakow. Let's change it one more time just so we can see what's happening. Emacs reservation service.properties. And I'll just now get it down to that, okay? Git commit -m, YOLO. Go, okay? So now I was able to change configuration live in the service while the service is running. That's the nice thing about the config server. I can centralize my configuration. I can use security. I can do all these kinds of things. The next thing I want to do is to make it easy for my service to find and work with other services. And for this, I'm going to use a service registry. And again, there's a lot of different service registries out there, but Spring Cloud provides a uniform abstraction that we can use to talk to a number of different service registries. I am going to use Netflix Eureka. I have Eureka here in the background. And I'm going to add the Spring Cloud Discovery Client abstract, the implementation for Eureka. That'll mean that the service is now accessible. It's discoverable by other microservices. And that's what we're going to do, is we're going to build a service that talks to our service via the service registry. We're going to build a client, and this is going to be an edge service. And this client will be written in Kotlin. So Eureka, this will be called the reservation-client. We're going to use the config client, use Eureka discovery support. We're going to use the actuator support. We're going to use Zipkin for distributed tracing. We're going to talk about Reactive, Spring Cloud Stream, and Kafka. We're going to use Hystrix, the circuit breaker. We're going to use a new project called Spring Cloud Gateway. We're going to use Reactive Spring Security. What else do we need in there, huh? Config, actuator, Zipkin, Kafka, Hystrix, gateway security, Redis. We want reactive Redis support. There we go. So we have a number of different choices that we're going to add to the application here, just as we did before. I think I'm happy with those choices. Do you think I need anything else? Reactive web support, surely. So there we are, reactive web. All right. So now, with that done, let's go to the downloads directory. UAO reservation-client.zip. And while that's starting up, let me go down to the bin directory here and start up a few other things that we're going to need. So Kafka, Zookeeper, Kafka.sh, Zipkin, run. Alrighty, good. So that's all running now. So we have our reservation client. We're going to comment out some of the stuff we don't need just yet, just for the moment. We're going to comment out Spring Cloud starter config. We're going to comment out the Zipkin and everything below that, okay? So here we are. So this is a Kotlin-based application. It's a little different than what you were expecting before if you've used Java. First of all, less code. That's kind of nice. Second of all, this is a function, and this is a class, but they are not related. This function is separate from this class. They don't need each other, right? That's actually a full class right there. And the function is a top-level thing. It doesn't sit at the same level as the class. Now, I'm going to create a edge service. Our edge service is the first port of call. It's where requests come in from the outside and actually talk to our downstream services. You might have a lot of different clients. You might have microservices that that have lots of different clients. Clients like iPhones, like PlayStations, like Xboxes, like Roku's, like HTML5 devices, like that one person using Windows Mobile. I mean, lots of different clients. And so we want to make sure that we don't have to change all of our microservices whenever we add a new client to the system. Instead of doing that, we're going to have a gateway, the API gateway, that will be the first port of call. We'll do things like change the incoming requests from the outside to accommodate the downstream microservices, okay? So this is a good place to use Spring Cloud Gateway. So we're going to use Spring Cloud Gateway here, using kind of like a Java-like syntax. We're using Java config here. I'm going to create a gateway bean, and this bean is going to, this method, this function is going to return a bean, an object type route locator. In order to create that route locator, I need a pointer to the route locator builder. And again, you could write this in Java. This would be public route locator gateway, and I would take a bean of type route locator builder, and I'm going to return that. So I'll say return rlb dot route dot route, and then we'll say dot build. Okay. Come back to this in a second, and we want to say curly bracket. There we are. Dot build. Now, there's our Kotlin code. And what's actually happening here is that in the second argument, in the second method function invocation, we are saying that we want to have a route that has a specification. Okay, so specification for the route, and the specification requires three things. It requires the incoming predicate, the match on the incoming request. I want to match all requests that go to /proxy on this port, right? I also want to match this host. So I want to say host equals .gw.sc, and I want to match this path. And then secondly, we want to specify what URL we want to proxy the request to, right? So spring.io :8000, or 80 in this case, guides. Very simple example, okay? So I'm creating a specification that matches anything on this host and this path, and it forwards that request to this guides. This is a proxy. This is a micro-proxy. It's a place for us to adapt the downstream services, to adapt the requests from the outside clients to the downstream services. And we can use this to do all sorts of interesting things by providing filters. And we'll come back to this filters thing in a minute, but let's go ahead and see what happens if we run this code right now. Now, oops, I have to get rid of the security for a moment. Don't do this in real life, but in my example, I'm going to get rid of security because I'm a terrible person. Here we go. Localhost. Sorry, it won't work on the browser anymore. We need this. Okay. Curl, HTTP, localhost. 9999 /proxy. So minus V will give us the visibility. Okay. So, oops. Oh, I forgot to give it a name. So Spring application name equals reservation - client. It's going to draw its configuration from the config server, just like before. Alrighty. So now, when I make that call, you can see it says 404 not found. I need to specify the host. So minus H host is equal to foo.gw.sc, okay? So now when I make that call, I get the HTML from the Spring IO guides page, okay? So that API gateway is working, and this is reactive. You cannot use Spring Cloud Gateway without the reactive support in Spring, okay? This is because this makes a lot of sense. What we don't want is to call another service and then get 5 terabytes of data, like a surprise, right? Spring Cloud Gateway can stream through the data reactively, as opposed to having to read it all to the end of the file and then fall over. Okay. Now this is a Java-like definition here, right? This is very close to Java code, but we can do much better. First of all, I have a function that's just returning an object. It's just doing one thing. It's got one expression, so I can get rid of all that. And get rid of that, and clean it up a little bit. I can just use a one-line expression like this. Also, I have a lambda here, a lambda argument, and it's the only argument of this route function. And in Kotlin, if you have a lambda, if it's the last argument, or if it's the only argument, well, first of all, if it's the last argument, then you can write that lambda outside of the function parameters, like this. Or, since this is the only argument, you can get rid of the function parameters, like that. I also have this lambda parameter called specification, and it's nice for visibility, but really, we already know what that is, and I don't want to have to type all that every single time. And if you have a lambda that takes one parameter, you can drop the explicit name and just use it. So it becomes it's the same thing as specification, same definition, right? Now, the other thing to keep in mind is that you can use certain APIs in Kotlin that are only available to you in Spring in Kotlin. So if you're using Spring and you haven't used, and you're using the Java APIs, you don't even see this stuff. They're already in the jars. They're just sitting there waiting for you to use them. But these are special APIs that are only visible if you're using Kotlin. It's like playing a video game and you find a secret level, right? These APIs are visible. So one thing that we can do is we can provide nice APIs that are only visible from within Kotlin, like this. All right? And when you do that, then you don't have to do all that other stuff I did. Okay. Route. Oh, we need to say route. Voila. Okay? So that's a Kotlin DSL that only works in Kotlin, but it makes our experience a little bit nicer. Now, this is pretty good, but it's a nice functional language. So rather than using Java config here, we can register things using functional bean definitions, functional bean registration. And you can do this in Java too. All you do is create an instance of application context initializer that's been genericized for generic application context. And then you can programmatically, you say it in this case is the generic application context, like this. You can say GAC register bean, and then the bean that I want to register is application runner, for example, whatever. I can just application runner class, and then I provide a supplier that provides a application runner instance. Hello. Okay, so that's the Java API that you can use, and this is supplier. There you are. That's the Java-like API that you can use from Java. But in Kotlin, there's a much nicer API that we can do because Kotlin supports these kinds of DSLs. So I'm going to say, add this initializer, beans, bean, and there we are. So bean is going to have a pointer. It's going to use this. It's going to be a route locator, basically. I'm going to build a route locator just like I did here. But in order for me to do that, I need a pointer to RLB. So I'm going to ask, I'll say val RLB equals ref to route locator builder. I'm telling the functional bean definition API to look up the reference to that, and then I'm using that here to create this bean object. Okay? Yeah. What is the problem? See, this is the nice thing about what we're doing here with beans. Beans, very good. And then that's a function. Is that right? And we can get rid of that and that. You see, thanks to Kotlin and functional Spring, we have brought the joys of parenthesis counting from Lisp to your life. Okay, there you go. So there's our updated code. And again, the nice thing about doing this is that it's this invocation here, this bean incantation, this is a function. So again, you can do some very interesting things that wouldn't be so easy to do with Java config. You can say, okay, if math.random is greater than 0.5, then call this function and register the bean, right? Or you can do a for loop, for example, right? Blah, blah, blah. So you can do all sorts of interesting things there in Kotlin that, in the functional registration model that wouldn't be so easy to do in Java config. Okay, now we have the same gateway. We have the same API gateway. Let's go ahead and start it up and see what happens. Okay. And if we go to the command line here, same result, good. Now, I want to change this service. I want to add a filter, right? And I also want to call the service in the registry. I have Eureka in the background. I want to call the registry. I want to get the resolved instances of the reservation service, and I want to call all the reservation service instances by using this URL. Well, this gateway is aware of our service registry because we have the Spring Cloud Discovery Client Abstraction implementation on the class path. That's this thing right here, the Spring Cloud Starter Netflix Eureka client. So we can do that here. And what I want to do is I want to use a filter. I'm going to say, okay, let's set a path. The target path will be reservations. Okay? So I can do all sorts of interesting things here. I can set request headers. I can set response headers. I can do a redirect. I can do a Hystrix circuit breaker. I can do a Spring retry. I can do all sorts of other things that are interesting here. One of my favorite things to do is to use a rate limiter. Now, a rate limiter is very useful if you have a downstream service that is fragile. It falls over easily. Maybe you've got some service that can't handle the scale, something that falls over a lot and you want to protect it, right? Maybe you've got some service that can only handle a very limited number of requests. Maybe you've got like a WebSphere install or something like that, and you want to protect it. So it can only handle 5 requests per year, right? So we're going to create a rate limiter that will keep track of the number of requests that are going to the downstream service. This rate limiter will protect our downstream service, okay? Now, in order to configure a rate limiter, you have to think about what the rate limiter does. A rate limiter keeps track of the number of requests that have come in, and then it keeps track of the number of requests that have come in, and then it keeps a budget, a count of those requests. And if the number of requests that it sees exceeds the number of requests that we want to allow it to have, it rejects those extra requests, okay? In order for us to have a consistent view of the number of requests that have been achieved so far per second, we need to store that number, that count, outside of the JVM code, outside of the JVM, and in some place where all the different clients can see it, right? So this edge service will be load balanced by the cloud, by the Elastic Load Balancer, the Cloud Controller, or something like this. We need to store it in some place where we can get access to that number in a consistent way across all consuming clients. Well, Redis is a great place to put that. So we're going to create a Redis-based rate limiter, okay? Bean, Redis rate limiter 5.7. So we're going to say Redis rate limiter, and we're going to use that Redis rate limiter here. We're going to say, it.rate limiter equals ref Redis rate limiter. So what that means is I'm going to use the rate limiter, which is going to allow 5 requests per second and then burst to 7 if needed. I'm going to use that rate limiter to restrict access to any endpoint that I want to protect, in this case, this path and this host. Now, think about what Redis is. Redis is a distributed data structure server. It's a big dictionary. It has keys and values. In order for us to keep that number, that atomic number, we have to have a key that we look at to determine, what the number of available slots, the available unused requests are. How do we resolve that key? Well, we provide a key resolver. So here is a key resolver. Very simple example. And I can just say flux.just my count. Okay? So there's my simple key resolver, just mono.just. Okay, so there's a very simple example. Now, this hard codes the key for all users. Well, that may not be what we want. If we are having a big sales holiday, maybe it's a Cyber Monday or Black Friday or something like this, or 11/11, Double Sticks Day in China. If you're having a big sales holiday, maybe those people in those geographies should have access to more bandwidth, more API requests per second, right? Because they're going to buy a lot. It's important. On the other hand, if you're an authenticated user, maybe you should be allowed to have more, right? As opposed to somebody who's not authenticated. Or maybe you're in a region where people are sleeping, and so there's not really a lot of you don't want to prioritize that region. You can scale down and then limit the number of bandwidth for a little while, for 6 hours, whatever, until people wake up in that region. So you can have a lot of dynamic factors that play into what key you should look into, right, for a given request. And so we can actually do all sorts of things here, but what I'm going to do is I'm going to use a key resolver that is aware of whether you are authenticated or not, like this. Principal key name resolver. Principal key name resolver looks at the current exchange, the server web exchange. It gets the Java security principal. It maps the principal to a string, and it says, if there's a string, great, use it, otherwise return empty. So when the rate limiter is looking for what key in the Redis database to look for, it'll ask this key resolver. Now, that is actually the default value, so I only show that to you because I care. I'm a giver. I'm going to go ahead and restart. And we're going to go ahead and start the application. And we're going to go see if this works, okay? So there's our application, HTTP 200. We have a bit of a problem here because we cannot have a rate limiter that needs the security if we don't have reactive Spring Security. So we need to use Spring Security to set up a reactive authorization and a reactive authentication. And we'll do this in two different beans. First, let's go back to our build and add Spring Security here. All right. So Spring Boot starter security. I'm going to say map reactive user detail service. We're going to do something terrible, something that you should never ever do. We're going to hard code some usernames and passwords. PW roles user dot build. Now, as I type this terrible code, Spring Security lead Rob Winch is sad. Don't make him sad. Don't hard code usernames and passwords. Okay? Oh yeah. Very cool. Thanks. So now we're going to use this hard-coded username and password, and then we have to manage. Now that we have authentication, we now need to manage authorization. Who can access the service? Who, once they're authenticated, what can they do? Okay. In order to do that, we need a pointer to the server security, right? Equals ref server HTTP security, and then we're going to use that builder API to set up authorization. I'm going to say I want to disable CSRF. I'm going to use HTTP basic, and I want to allow any exchange to go through, except I want the exchange, the URL for proxy, to be authenticated. And then finally, I'll build. Now, this is a good time to talk about a convenience feature in IntelliJ that makes it a little bit less painful to write this kind of code, and that is @formatter off. Now, this is from Eclipse, and it was added to IntelliJ later on. But the benefit is that if I format this code here, for example, and then hit reformat, this gets left alone, which I think is very convenient. Now, let's go ahead and restart again. Alrighty, so 401 unauthorized when I make the request, right? I need to do authorization, great, so we'll say user PW, and when I do that, I get the data. There's the JSON that we got back from our server that's been load balanced by calling the service registry. So now we have the data, and let's drive some traffic. So while true, do, and then done. Oh, sorry, let me get rid of JQ here. Okay, so I'm driving some traffic as fast as I can. You can see that this request is 429 too many requests. This one is 429 too many requests. This one's 429 too many requests, etc. But this one is 200 JSON, right? We got the JSON back. So we have a rate limiter that's rejecting requests that are, that exceed some budget, some criteria. Okay, so that's an API gateway. That's a very simple thing to do. This is a brand new project. Spring Cloud Gateway is a brand new project in Spring Cloud Finchley. It is we consider it a successor to Zool, for example. If you've ever used Zool, Zool had some problems that make it less than ideal for what we're trying to do here. First of all, it didn't support the reactive stream specification. Second of all, it didn't support other protocols besides HTTP. Third of all, there are some important pieces that were missing, like, for example, the Redis rate limiter, right, or like rate limiters in general. So all of this is now something that we can provide a fix for you out of the box. This is a generic API gateway, but a lot of times we want to do things that are not just API gateways. We want to actually synthesize new endpoints. We want to take the data from downstream service and combine it into a new endpoint that we can then consume. And in order to do this, we need to have an awareness of the data that we're sending over the wire. So let's create a new endpoint here using the Kotlin DSL for creating reactive functional reactive web endpoints. We could use the router function stuff. Remember I showed you that before? We could use that, and we're going to use the same thing, but there's a nice DSL in Spring Framework 5 using Kotlin. So I can say router get reservations / names server response.ok.body, and the body is going to come from a reference to the data in the database. So I'm going to say ref reservation repository. Val, we need a reference to the HTTP web client, the reactive web client. And we're going to come to that in a second, but I need to actually have that there in order to get my response here. So let's val body, or reservations, and we'll come back to that in a second. We need to create a pointer. We need a reference to that web client. So we're going to create a reactive HTTP client like this, builder.filter, and we're going to inject the load balancing exchange filter function, like so. Build. Okay, so this is a reactive HTTP client. We could use the REST template, but it's not a great fit for what we're trying to do. So instead, we're going to use this reactive HTTP client instead. And that HTTP client we can use to make this call. We're going to say client or client dot get dot retrieve dot body to flux, and we're going to turn this into a payload of type reservation. Okay, class reservation, and we're going to create a client-side representation of the data. Val ID string != null. Val reservation name string != null. So I'm going to create a client-side representation. This is the same thing as that entity that we looked at before. It has a getters, setters, equals, hash code, toString, all that kind of stuff. It's just much more concise, much more succinct in Kotlin. Okay. So with that there, we're going to say take that data and turn it into a payload. Take the response, the JSON response, turn it into a publisher of type reservation. And I'm going to map each one. And I'm going to unpack the reservation names. So what I have here is a body that is a publisher of string names. Okay? So pass this here, or body. Come on. There we are. So I'm using an overload version of this as well. In the previous version in Java, you had to see, you can remember I had to do a class literal as the second argument. I had to say, for example, string class. Well, in Kotlin, we can have a quasi sort of reified generics syntax. So that gives us the ability to use this, and we don't have to specify that generic type. Okay, so now that should work. I mean, it seems okay. Oh, we need the URL as well. So URL equals reservation - service reservations. And this right here is the host name. This host name is because of this. We understand what that host name is by going to the service registry. In order to do that, we have to have this filter configured on the web client. So when we do that, we get back the JSON, and then we take the JSON, we unpack the reservation name, and then we turn that into the response that we see there. So let's go ahead and start the application, see what we get. Okay. Localhost 9999 reservation names. There we are. There's our names. And that seems to work okay, but there's a serious problem with this code. This code, as it's written, is assuming that everything will be fine and that this service will always be available, that the instances of the reservation service will always be in the registry. But that's not always true, is it? What happens if there are no instances of that service in the service registry? I can't load balance across all those different instances, can I? If there's nothing there. You can't load balance across 0, just like you can't divide by 0, can you? You know what 0 divided by 0 is, my friends? Hey Siri, what is 0 divided by 0?
Imagine that you have 0 cookies, and you split them evenly among 0 friends. How many cookies does each person get? C. It doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
It's true. Don't make Cookie Monster sad. High-performing organizations understand the fact that things will fail. It's not a matter of if, it's a matter of when. And we need to build our systems accordingly. We can't just leave this code as is because it might fail. So we need to be a little bit more robust in the way we handle that. One way to do that is to use a circuit breaker. So I'm going to use Hystrix. Hystrix is a circuit breaker from Netflix. We're going to wrap this body, give it a fallback value here. We're going to say flux.just eek, for example. We're going to give it a command name. Just going to call that names. And we're going to build it, okay? And I'm going to send that instead. I'll send that circuit breaker instead. And there we go. Alrighty. So now, if I make the call again, whoops, wrong one, curl HTTP localhost 9999/reservations/names. Okay, there's the data again, no problem. Now let's go kill the downstream service, this one here. Goodbye. Okay, there we go. We got the circuit breaker. What we got is the value that we expected, not something else. We controlled what we got back here, right? What we didn't get is a big fat Java stack trace. What we didn't get is an ASCII art middle finger rendered for us, right? In our poor iPhone user experience. We controlled the response that we got back here. This is graceful degradation. And this is the read use case. I'm reading data from the downstream service. And so this works just fine. What about write? What if I'm writing data to the downstream service? What happens then? How do I guarantee that the system does the right thing in the face of service outages and topology changes when I write data? There's a lot of different things we could talk about here. What we're trying to do is to get one service to agree with another one. We're trying to get them to be consistent. Two different nodes separated possibly by a network partition. There's a lot of different ways to solve this problem. One way that is not a good solution to solve this problem is JTA. JTA is the client-side middleware for the XOpen protocol. The XOpen protocol is completely irrelevant here, right? My REST API doesn't speak the XOpen protocol. MongoDB doesn't speak the XOpen protocol. So these are not good solutions. I want to send data from one node to another. And again, I can't just post the data, right? Let's say I have an endpoint here in my Kotlin endpoint. Let's say I create another endpoint here, post, just reservations. And here's the incoming request, right? I can call it, but that's the request. What do I do now? To do. Send post from edge to reservation service. How does that work? Well, I cannot just use the client and do a post. There may not be any reservation service to send this message to, right? What happens then? I'm just going to drop the messages on the floor? Just drop the state on the floor and lose the data? This isn't MongoDB. We can't just lose data, right? We can't just take something that doesn't belong to us and run away with it. Even a 4-year-old child knows this, Mongo. We must do better. We can look at a number of different patterns to support what we're trying to do here. We can look at eventual consistency, which is just a fancy way of saying messaging. Nothing fancy about this at all. We can use the Saga pattern, which is a pattern from the 1980s, right? Very old pattern that would serve us just fine here. We could use CQRS and event sourcing, which is a great approach. It's a little more than we want to do for this particular example, but all these are great things you should look into. For our purposes, however, it's just fine to use messaging. And so in order to do that, we're going to use Spring Cloud Stream. Spring Cloud Stream lets us declaratively create the bindings from our code to the other node and have that wiring, have that relationship as a matter of configuration, not explicit code that we have to worry about. I'm going to bring in Spring Cloud Stream Kafka and the Spring Cloud Reactive support. And what I'm going to do is I'm going to create a binding to my downstream service. And the way you do that is you create an interface. So producer channels, for example, output, fun message, or fun output. And it's going to be a binding that allows me to send messages into an output channel. A channel is a pipe. It's a named conduit. Data in, data out. I can do this like this, and I can say to Spring Cloud Stream, I say @enable binding, producer, channels, class. Okay? That certainly works. But is that, do I need to create this interface just for one channel? If you have multiple microservices, then you could create multiple channel definitions. You could say the customer service is here, and then another one for the order service, et cetera, et cetera, et cetera. And you can have as many channel definitions as you want. All we need to know is that if you put a message into this channel, it'll eventually be delivered to the microservice called orders. And we'll talk about how that happens in a second. It's a matter of configuration. For our purposes, though, we can leave it like this. This is such a common configuration. There's actually one that's already pre-written for us called source. So source. There we are, source. Spring Cloud Stream Release, source. And the source channel, source definition, has a defined output channel already that we can use. So I'm going to say, use that instead. I'll say @enable binding source. Okay? It's the same thing as what we just did. It's just already pre-written, which is nice. Good. Now, with that source definition, we can inject a pointer to that output channel, source. Source equals ref source. All right? Now, what I'm going to do is I'm going to say source dot output dot send, and I want to send a message when the request comes in. So I'm going to say take the request, take the incoming value, so the body, okay, to Flux. I'm going to turn it into a publisher of type reservation. Take the JSON that's going to be posted to the edge service, turn it into a reservation, like so. Come on. All right. Map each one of those to a reservation name, or actually to a message, actually. I'm going to send it as a message. So message builder dot with payload it dot reservation name dot build. And we're going to map each one of those and send it on the output channel. So source dot output dot send it, where it is the message of string. Okay? So that's all we're doing. Whenever somebody posts, we're going to do all this. And the result of this, of course, is a publisher of Boolean. That's the value that you get when you send something. So sent publisher of Boolean. All right. And that's actually a flat map. Okay. Good. And we want to say server response dot okay dot body equals sent. Is it just map? I think it's just map. Very good. Okay, so we're building a message with a payload. The payload is the string. We have a bit of a confusion here. The payload here is expecting a non-null argument. But in Kotlin, the nullability of a variable is part of the compiler. The compiler cares about that. So you need to be very explicit about how you do this. My favorite way to solve this problem is just to yell at the compiler like this. Right? Alternatively, you can use the Elvis operator. You know the American singer Elvis? Huh, right? He's got the hair, so you can, default, whatever. And the reason it's called the Elvis operator is because if you look sideways, it looks kind of like Elvis, right? But I prefer to tell the compiler just to trust me. So I yell. Okay, so that's the post from the edge service to the downstream service. That's going to be delivered to Kafka. I've got Kafka running in the background. We're going to talk about that in a second. Let's go do the same thing. Let's configure the opposite code on the other side when the data is delivered and we want to process it. So here on the consumer side in Java code, I'll do the same thing in reverse. I'll say @enable binding, POM. I'll bring in this dependency here. Alrighty. So there's this. And I'm going to say @enable binding sync.class. Alrighty. Okay. And in the incoming code, what we're going to do is we're going to say, when the message arrives, public void incoming or process. And what I want to say, I want to process the data coming in on the input channel called sync. And we'll look at that in a second. Incoming. This interface is the same thing in reverse, except instead of an output channel, it has an input channel. And it says, I have a subscribable input channel. I'm going to tell Spring Cloud Stream to give me those records as a reactive publisher. So each time a new message arrives from Kafka, then the publisher will emit a new item. So I can now say incoming dot map string. I'm going to turn the string into a new reservation. Null for the ID, S for the thing there. I'm going to then flat map each one of those and save it into the database by using the reservation repository that we have here. So private final reservation repository, RR. Alrighty. This.rr.save. And we're going to say R. Very good. So there's that. And then I want to finally subscribe. I want to say I want to print out the confirmation. So saved, system out, print line, saved, save.get reservation name with ID saved.get ID. Okay? So that's this functional consumer. It's a reactive consumer here using Spring Cloud Stream. And that's it. Let's go ahead and restart this with all the code in the class path now. And let's go ahead and try it out. So curl HTTP localhost 9999/reservations. I'm going to send an HTTP post with a body, and we'll send the body in a second, but it's going to be a content type application JSON. And we'll say reservation name equals, and we'll send some of my favorite doctors, Doctor Who. Okay. So now here on the consumer, you can see it already says save Doctor Who, right? And then I'll say send Dr. Strange. Okay, and there's Dr. Strange. So as we post to the edge service on port 9999, our node running on port 8000 is receiving those messages from Kafka. Now, that's the happy path. Everything is going according to plan, right? Let's try the unhappy path. Let's go kill the reservation service here. This is the reservation service. We're going to kill this. And now we're going to send some more data. Dr. Subramaniam. Some of my favorite doctors. Dr. Dave Sire. Okay? Spring Boot and Spring Cloud co-founder. So, we've got that. This application has been killed. I killed it. Let's go ahead and restart. Alrighty. So there we are. There's Dr. Sire and Subramaniam reporting for duty. Okay? So that we were able to process the missed messages automatically. Spring Cloud Stream makes sure that we get useful defaults out of the box. The result is that now we have an application that does the right thing for both reads and writes. If I write data and it fails, it'll do the right thing. If I read data, it'll do the right thing. I'm using Spring Cloud Stream for the write. I'm using the circuit breaker for the read. Okay. Now then, we have an application. We used Spring Cloud Stream to make that last thing a little bit more resilient. Let's look at the config for that. In order to understand what's happening, we need to go to the config and the config server. And here it says Spring Cloud Stream bindings.output.destination. Output is the name of the channel in the interface, right? The binding channel. It says output.destination equals reservations. This is the topic in Kafka. Right? Both producer and consumer need to agree on this. But this is the channel name in Java code or JVM code, right? This is unique to your Java application or your code. They don't have to agree on that. So on the consumer side, the service which receives the messages and writes the messages to the database, here it says Spring Cloud Stream bindings.input.destination equals reservations. We also want to make sure that we don't miss any messages. So we've said that the input binding is durable. And finally, we've also said that we want to make sure that we can do load balancing. Instead of broadcast, instead of one to many, we want to do many to, we want to do, we want to be able to send X number of records and then divide that by the number of consumers. So we say that any consumer that is part of the same group gets only one message at a time. Instead of all consumers all getting the same message, only one consumer gets one message, okay? Even if you have 10 consumers. And that's what this group thing is. That's why this is, that explains all this behavior that you've seen here. So now we've got an application. It's up and running. We looked at observability a little while ago in the first segment. We looked at observability using the actuator. And the actuator gives us the ability to understand what the application is doing on an individual level, at an individual level. But it doesn't tell us about the system as a whole. It doesn't give us the ability to understand what the whole system is doing. So rather than just looking at the actuator endpoints for that information, we can use Zipkin. Zipkin is a distributed tracing platform that gives us this visibility. I have Zipkin running in the background here. Okay, so Zipkin is running in the background, and it knows about the different endpoints that I've got in my application. It is using Kafka as well to receive this trace information and to then put that into a big picture that we can then see here in the background. I can make some if I make some requests. Well, I've just done a whole bunch of traffic actually. We'll go here, reservation client, reservations, hit find trace, and I can see all the different requests that have gone through the system. I can click on one of these requests, and I can see it took 16 milliseconds, and the request arrived from the reservation client. It went to different nodes. It passed eventually into the reservation service. And if I click on any one of these, I can see the details of that trace, right? This gives me an idea of what the system as a whole is doing. This is one way to get observability. Remember, at the end of the day, our system is more than just individual nodes in the application. It is the emergent behavior of the whole system itself. In order to understand that emergent behavior, you need to be able to draw a picture like this. You need to be able to understand what the whole system is doing. Zipkin and Spring Cloud Sleuth make that possible. We have this on the class path here. It says Spring Cloud. Where did I put it? Zipkin. Spring Cloud Starter Zipkin. That's automatically publishing messages to Zipkin over Kafka. And it just does it for you. For all the messages that flow through your system, whether it's through an HTTP endpoint, through data, through messaging, through Kafka, through whatever, these messages come and go as they need to. Now, there's other ways you could capture observability. Certainly, we could talk about this all day and long, but we have about 10 minutes, and I want to show you one last thing. I want to talk about one special category of application. So far, what we've looked at is a microservice-based approach to building this this particular arrangement. We have an edge service and we have a back-end service, and they're using other bits of infrastructure. There's a config server, a service registry. We've got Kafka. We've got MongoDB. We've got Redis. Lots of other satellite things or services that are serving our application. And the application itself is it's always running, right? The edge service, of course, is a natural thing to always have running. But the edge service is not the it is the front end for the application. It is where requests will arrive in the system. But the back end, in this case, is also always running. And that's fine in this case because we expect fast results from the back end. But there are a lot of workloads that are slightly asynchronous. They take a little longer, and they shouldn't be in the front end, hot path of your request processing chain. Things that we used to talk about as being back office, right? Things like email, if you want to send an email, if you want to resize an image or produce a report, or any of these things that should get done, but you don't want to waste your threads on your thread in your web server trying to do these processes. They should live on some other node where the slowness can be scaled out horizontally using messaging. And so this kind of work is a very common thing, and yet it's not pleasant to have to set this all up. You have to set up a message queue. You have to connect the message queue to the applications. You have to write code using Spring Cloud Stream, etc. And also, you have to deploy all this, right? So you have a lot of management overhead, not just in operational terms, but also in code, right? Well, there is a way to sort of, if we understand that we want this kind of use case, this kind of paradigm, there are ways to write code that serves this use case. These days, a lot of platforms support something called serverless or function as a service platforms. How many of you have heard of function as a service? Like AWS Lambda, right? Or something like this. Well, we have a serverless platform called Project Riff. Project Riff is an open source Apache 2 licensed serverless platform. It's a function as a service platform that supports many different languages like Go and Python and JavaScript and Node and Java, of course. And this runs on Kubernetes. You can run it in your own data center. You can run it in your own machine. You can run it on Google Cloud. You can run it wherever you want. And I have Project Riff running in the background here. So if I look at this, Riff here, and I say I want to delete this, Riff delete name up minus all, it's in the background there. And what I want to do is I want to deploy a function, just a very simple function since we have very little time, using Spring Cloud Function. Spring Cloud Function is our new function as a service abstraction. It supports Project Riff, but it also supports AWS Lambda. It also supports Microsoft Azure. It supports OpenWhisk. I mean, it supports a number of different runtimes here. So we're going to create a simple function here. I'm going to use the config client just to add the dependency to the class path, but we don't actually need that. I'll change it in the POM. Right now, there is no checkbox for Spring Cloud Function. So cd downloads, UAO, uppercase. Okay, uppercase application, and all this is going to do is it's going to use Spring Cloud Starter Function Web. Okay, so I'm going to bring in the Spring Cloud Function support from Project Riff, from Spring Cloud Finchley, and we're going to create a very simple function, just as simple as we can get it. We need Spring Boot Starter. Okay, now bean function, and we're actually creating a Java util function here, right? A regular old function. Spring Cloud Starter. Thank you. Way to pair program. All right. Flux of string uppercase. Okay, so this is a very simple example. Alrighty. Whew. Now, all we're going to do is we're going to say whenever a new message arrives from Kafka in this function as a service platform, which is using Kafka behind the scenes, you don't have to worry about that. We're going to take the incoming string and then map it so that it's uppercased. Okay? Now this, of course, cleans up nicely. It can replace with method references and so on. And there's our function as a service. Okay? Very simple. Now, I'm going to deploy this function to Project Riff. So cd uppercase maven clean package. And here, I'm going to eval. I've got Riff running on Minikube on my local machine here. Docker env. Okay, good. And that's been built, good. So let's go back to that. Now I'm going to say Riff create Java -a. I'm going to give it the Kafka queue on which messages will arrive. I have to give it a logical name. I'm going to call it up. The name of the function, I'll just call it up as well. The artifact that I want to run, I want the jar or my Go program or my Python program or my Node.js program. I have to give it the artifact. In this case, it's my jar. And the handler is just the name of the bean. In this case, uppercase, right? Uppercase is the name of the function. And with that, I'll deploy it to Riff. And if I look at this, I say Riff list shows me the functions running. What the? 10 minutes. Riff delete all up name up. Riff list. Okay. Whew. That was weird. Let's try again. Okay. There we are. Riff list. There we go. 10 minutes. Whatever. Okay. It's so fast it goes back in time. So I'm going to say publish a record. I'm going to publish a request on the input Kafka topic called up. The payload will be a string, hello, Krakow, and then I'm going to ask for a response to come back. Okay? It's going to publish to the gateway, to the edge of my Riff installation. I'm running it on my local machine inside of a virtual machine. You can use PKS or Pivotal Kubernetes Service. You can use GKE. You can use whatever you want, right? And as soon as the first time it starts up, it takes a few seconds because it has to load the container. Then, as I make subsequent requests, it goes fast because it's loaded. It's hot. But as soon as you stop making requests, as soon as you let it go, like for 15 seconds or more, then it scales down to 0 again. So you're not running anything you don't need. Okay. Now, in this case, I used an input channel. I used an input. I specified an input Kafka topic here. I could have also specified an output one. So I could say -o is reverse or something like that. So you could actually have a number of, and then you could have another function where its input is reverse. So you can string together these functions and do these stream processing pipelines spread across a number of different nodes and staged or buffered by these brokers. All right, my friends, we've looked at just a few things today. Just a few things. We looked at a few things in terms of reactive programming. The whole point of all this is to show you that when you use reactive programming, you get ultimately a better result in the case of having something that is I/O bound and something where it exceeds the request arrival rate. So if your requests arrive at your web server faster than you can produce responses, then you're going to care about reactive programming. I hope you got something out of this. I hope you saw something here that you hadn't seen before. We covered a whole bunch of new stuff. So Reactive Spring, the Reactive Spring Framework 5 support, Reactive Spring Data, Reactive Spring Security 5. We talked about Reactive Spring Cloud Finchley, including the brand new project Spring Cloud Function and Spring Cloud Gateway. We looked at the reliability patterns like eventual consistency and messaging. We looked at the reactive support in Spring Cloud Stream. We looked at a number of different things here today, and I hope you liked what you saw here. You got something out of it. I want to thank you so much for coming. Jinkuya, thank you so much, my friends. If you have any questions, I'm happy to answer them.